Hello everyone. Sorry for the delay. We'll be beginning in another 5 minutes.
Hey Aryan, so I guess you can move all the attendees to the panelists because some of them are authors. So we are sorry everyone. So the previous session has almost about to end. So I think we can wait for another 2 minutes and we can get started. Thank you.
Everybody is in the panelists list now. Uh,
So I think we can get started. Meanwhile, other participants will join once the previous session is over. I believe they will join soon. So the first speaker is Dong Hao. So Aryan, please make him presenter so that he can present his paper.
对，马上开始。
yes, sir, just a second. Piyush, can you make him the presenter?
Oh, yeah, sure.
Yeah. Okay. Okay. Can we start?
Yeah, please start. So you have 17 minutes to present your paper and probably last 2-3 minutes for the question answer.
Okay. So, good afternoon, everyone. My name is Dong Zhen. Glad to be here to introduce my work, the unsupervised generative adversary alignment representation for sheet music, audio, and Linux. So this is the outline of this presentation. Firstly, I will show the introduction, which include the background, the goal, and the novelty and the contributions. And then I will explain the architecture in detail, and then show the experiments and some results. Finally, I will make a conclusion of this presentation. So, to firstly, I would like to introduce about cross-modal retrieval. So it is which is use the data from one modality to search the data from another modality. So one solution of the cross-modal retrieval is to build the concept alignment between the data from different modality, which is also used in the multimodal information retrieval. So as for the concept, for example, when we use a sentence which have the keywords cat, so we want to find the relevant image. So the image would the expected image should contain the cat. So we can name this kind of concept like a cat, dog, or kids is the explicit concept. Except that when we want to learn the content based high-level semantic alignment, we can call this, because this kind of the alignment is didn't have the explicit concept, so we named it. It's kind of is implicit concept. So the gap in the implicit concept alignment for the multimodal information retrieval, firstly, is the heterogeneous gap. Because the wider use the low-level feature of different modality pose inconsistent distribution and representation, which may cause the feature unable to be directly compared with each other to do. So we need to map the data from different modality into a common space that the dimension is the same. So we can compare it with each other directly. So the second one is that the concept alignment is constrained on the two modality, like a cross-modal retrieval. So, so the goal of this work is to bridge the heterogeneous gap among the three modality in only one common space. Okay. So in this work, we collect a new music dataset, which include music audio, the sheet music, and the Linux. And also the audio and the sheet music pair is known, and the audio and the Linux and sheet music and Linux is unknown. And also we propose a new architecture. So as the figure shows that audio and the sheet music, the pair is known, and another two pairs is unknown. So the novelty of this work, the model can transfer the known relationship between audio and sheet to the audio and Linux and sheet music and the Linux pair by learning the correction in the lantern shell subspace. So a contribution of this work, firstly, it can transfer by the game. Yeah. And the model on the music dataset prove that feasible of learning the alignment between different modality. And the work in detail is combine the CCA projection with the optimal implementation of the GAN model to establish use the CCA to establish the new ground truth and explore the genetic model to generate a new audio sheet music to fool the discriminative model. And also we collect a new music dataset with 3 modality. So firstly, we would like to introduce about a generative model. It's one important model of the game. So the goal of this model is to generate a new audio and sheet music pair with a fixed lineage to fool the discriminative model. So this model have 2 steps. Firstly, we do the alignment learning by the model transfer with the teacher and the student model. We assume that Linux is a teacher model because it tried by the script grammar model. It have the semantic representation. So we expect that audio and sheet music as a student model also can learn the semantic representation from the Linux. So the model transfer is founded by the KL divergency loss, which in this step enhance all the modality have the similarity representation if they are paired. So the second step is the alignment learning by the generative probability. So given Linux, the generative model add at fitting the contribution of the Linux audio and the Linux sheet music pair in a common space by mapping the function into a common space. Then the pair of informative audio and the sheet music are selected to test the ability of the discriminative model. So the generative probability of the G model is the foundation of selecting the relevant audio and sheet music pair from the unpaired data with Linux. For instance, give a Linux as query. The generative model try to select relevant audio and the sheet music from that base. So here, this possibility decide whether the possibility of the audio and sheet music pair is relevant or not. So another important dataset model is the discriminative model. We apply the KM math to explore the underlying manifold structure for CCA embedding of the audio and sheet music pair, and we select the top 5 most close items to establish new pairs as ground truth. And the input of the discriminating model is generated audio and sheet music pair, and the manifold structure based on ground truth. So this the target of this model is to distinguish the input pair is from ground truth or is generated by relevant score or the judgment score. So once we get the 2 model, we use adversary learning to conduct the minimal max gain. So the architecture including 3 parts: the feature extraction, a genetic model, and discriminating model. Firstly, in the feature extraction, we use a pre-trained model to extract a feature. We use the VGG for audio feature extraction and Wiggins-like model, the Inception Vision 3, to extract the sheet music model, sheet music feature, and use the skip ground model to extract the Linux features. and then the genetic model can generate the audio and the sheet music pairs, and each pair they have a genetic probability, and the probability is to decide whether the pairs is informatic or not enough informatic, and we select the informatic pairs to input as the input of the discriminative model, and the discriminative model have the CCFS ground truth and the output of the G model. So the data collection, our music dataset is followed by another work in our group. This work is they have the music note and the linears paired, but yeah, the linears is the syllable structure. So we do some processing. We select the former 20 notes for each sample and remove the reset. It's longer than 4 seconds. You know, the music note, they have 3 components. The pinch is the high and the low end of a musical note. The duration is the time span of its note, and reset is the interval of the 2 connected musical note. So once we get the 20 notes here, we use some technique to generate audio and sheet music. We synthesizing audio with the timidity pass technique and created the sheet music by Lee Pond. Okay, see, here is some samples of each the data. In the experiments, we apply some metrics for the information cross-modal retrieval, like record K, record AK, and median rank and mean rank. So firstly, we decide some baseline. The first is baseline. We named it baseline. It's only discriminant model without the G model and without the adversary learning. The second is baseline. Again, is an extension of the baseline. It has the D model and adversary learning. So in the table 1, the cross-modal retrieval result on the dataset, we can see, for example, audio to retrieval linears. The record at 1, you can get around 1% improved, and the median rank you can get 90%, 90 improved. So this result can show that the effective or proposed model for transfer learning from the audio sheet music pair to the another 2 pairs. So in table 2, it shows some cross-modal retrieval result compared with a random case. So in general, we can conclude that our model is feasibility of a further improvement of the proposed model in general. So the results suggest that our model is a rare ability to learn the alignment representation. But the experiments only show some initial result, so they have some shortage here. The first one, as I know, is like the generative probability in the generative model is too weak to generate a new pairs. I guess because I only consider the relevant position of the audio and the sheet music in generative model training. And one solution is that we should consider local positions. Another reason probably is that because some ways of the network is code zero, so maybe we need to do some professional data processing. So, uh, so in this work, we because the learning alignment implementation between two modality has get outstanding achievement. So in this paper, we develop architecture. It's about representation learning on the same modality to learn the alignment by the modality level transfer learning. So the experiments results show that the feasibility for aligned representation learning across the three different musical modalities. Yeah, thank you for attention.
Thank you. So we have time for probably one question.
Yeah.
Anyone? Okay, if not, then in the interest of time, let's move to the next presentation.
Yeah.
So I believe Vivek will be presenting. Is that you, Vivek, or someone else?
Mm-hmm.
Vivek, will you be presenting the next paper? Yeah, good.
Yeah,
Yeah,
that's me.
wonderful. So Aryan, please make Vivek as a presenter.
Oh, yes, sir, I have done it.
All right. Good afternoon, everyone. My name is Vivek Singh, and it's my pleasure to present this work. This is joint work with Jamal Al-Asadi, Ramnathan Arunachalam, and Pradeep Atre. Our work is titled A Fairness-Aware Fusion Framework for Multimodal Cyberbullying Detection. What we mean by these things, I will talk about it in the next few slides. So broadly speaking, our work contributes to the literature on algorithmic fairness. Algorithmic fairness is this idea that algorithms, when they affect people, when they affect society, it should be equitable to different sections of the society. For instance, this report coming out of ProPublica said that early prison release, basically parole system, it was being done using an algorithm in New York State, and it was systematically biased against people of color. For roughly the same credentials, it would give very different outcomes depending on the race of the defendant. And that's problematic because algorithms can scale this up and can amplify the biases which exist in the society. And as computer scientists, we would not like to see that happen. Same things or very similar things have been shown in other domains. For instance, this is face recognition, or rather characterizing certain properties based on faces of people. And this New York Times article said that face recognition is accurate, well, if you are a white guy. So what these researchers had found was that face analysis worked very differently depending on the race and gender of the people. For white men, it performed the best. Next were white women, then male, but people of color, and lastly, people of color who were also women. So again, this is something that you would not expect to change based on demographic characteristics, but a computer algorithm was performing differently for different sections of the society. And this happens even in text processing. For instance, this is Google Translate, or an older version. I think they've tried to fix this now. from Turkish to English, where there are no connotations associated to with gender, like this person is a doctor, but when it was being translated, Google Translate automatically somehow assumed that a doctor was a he and a nurse was a she. Again, these things are going to amplify biases, lead to further downstream effects, and so on. And we want to both audit for these things and counter these things. Now, this may come across as a little bit of an abstract concept, but this literature has been growing steadily, and people have defined number of metrics to quantify what is fair and what is unfair. At least for the purposes of our discussion, we are focusing on machine learning context and what some basic things which you would expect, which are part of the literature, what we have also adopted, is that you would expect equal accuracy or some measure of accuracy. Could be, let's say, UCROC, F1 measure or something. It has to be equal for the different demographic groups. Let's say if we are focusing on binary gender, which again has its own limitations, but let's say we are focused on binary gender, then you would expect equal accuracy for men as well as women. It shouldn't be that for men you get 90% accuracy and then for women only 50%, then that delta of 40%, that's problematic. And we want to shrink it to as little as possible. Same kind of thing people have studied, and they've argued the case for equal true positive rate, that at least for the deserving instances, let's say you were giving college admissions using a machine learning algorithm, at least for the deserving cases, you should get that TPR, true positive rate, equal for different groups. Some people have argued further that, well, you should also make sure that the FPR, the false positive rate, is equal for the different demographic groups. So we'll be adopting those interpretations of bias or fairness. So coming back to the problem that we are tackling, that is of cyberbullying detection. So now what is cyberbullying? Cyberbullying is when the internet, cell phones, or other devices are used to send or post text or images intended to hurt or embarrass another person. Basically, you cause somebody else harm using technology. What is fusion, or rather the traditional interpretation of fusion? It is that you are combining data from multiple modalities to increase the accuracy of the overall decision. So there's sensor one, which says that there is bullying going on with 80% confidence, another sensor which says that there's no bullying going on with 60% confidence, and you could somehow combine these two together to get as high an accuracy as possible. So what we are bringing to the table is this idea of fairness-aware fusion. How it differs from the traditional fusion is that we say that we want to combine multiple modalities, but not just to increase accuracy, but also increase fairness. In effect, what it turns out to be is like it's some kind of a trade-off, a combination between accuracy and fairness, but both should be important criteria to be considered before you make your final decision. That's what we are trying to argue for. To do this, we studied a data set of Instagram posts. So it was the post, the text by the original poster, as well as other people comments. Together, this thing is known as what is known as a media session in Instagram. And there was human labeling of bullying. There were visual features, there were textual features, and the overarching approach that we have is that of Bayesian fusion. Again, you could actually combine different modalities using very simple things too. You could, let's say, do a voting, you could do a weighted average, things like that. Bayesian fusion tries to kind of optimize on some of those parameters. So our contributions for this work first, we are the first group, as far as we know, to audit this application space of multimodal cyberbullying detection. We are not aware of any other work which has tried to study this question, that when you do multimodal cyberbullying detection, how are different sections of the society affected? For instance, men versus women. The next thing which we do is we propose a fairness-aware framework. Specifically, it's a Bayesian fusion framework for reducing bias. That's our goal. So the delta, if it was 90%, our hope is that we shrink it down to like 1%, or well, as close to zero as we can. So this probabilistic fusion framework that we are adopting, it has two important components. The first one is that we need to come up with a confidence score of a modality. The second is an agreement coefficient between modalities. So what I mean by confidence score in a modality is, I was just talking about two sensors. Let's say one is a visual sensor, one is an audio sensor. And in the past, one has been 80% accurate, the other one only 60% accurate. So you'll have different kind of confidence scores, how much you trust each of these sensors. That's the confidence score. The second thing is that there is an agreement coefficient between sensors. And now imagine instead of two, you have, let's say, 9 different sensors, but two of them almost always say the same thing. Now, if you were to take their votes, you will give it lesser credence because, well, these people seem to always agree. If one has said, and I know that, there's no new information that I will get by looking at the other. So we will be using these two things, the confidence which we have in each sensor or modality or feature, which we are kind of using interchangeably in this work, and the agreement coefficients between these features. So we also had to do all of this in a fairness aware manner, right? So what we did was we considered two things. To get the confidence score for each feature or modality, we looked at their training accuracy. That gave a score for accuracy. Let's say that training accuracy was 80%. So higher the accuracy, the higher that feature should get. But we considered a second aspect, which is that of fairness of that modality. So it could average 80%, but if it was, let's say, 99% for men and only 59% for women, that's problematic. So that's about 30% gap, right? So if we will basically deduct some score from this average, which we have based on the delta that we observe for the different demographic groups that we are considering. How do we combine the two? We simply take like a weighted combination. So this parameter lambda is going to kind of dictate how much importance we want to give to accuracy versus bias when we decide how useful or important this feature is. Once we have these scores for a single feature, we can start combining these across multiple features. Basically, this is a kind of a normalization. This is what has been used in past literature on Bayesian fusion. And then you have groups. So like the first two features will become one group, and then you add the third feature to that group, or you could have 3 features and now you add the 4th feature to that group. So basically you can iterate and expand the pool of all the features that you're considering, and you'll get like a joint weight for all those features. So this was the weight, the confidence which you had in different features. We also need to consider the agreement coefficient. For this, again, we use something pretty standard in the literature, which is Pearson's moment correlation, which gives you a sense of how similar these two sensors or modalities have been in the past, and that gives you that agreement score. Now, if we have all these things in place, what we can do is we can compute the probability of cyberbullying as follows. So probability. So we are collecting the positive evidence for cyberbullying. So P plus, that is the probability of detecting cyberbullying C, given that feature I is whatever it is. So for instance, if the text length is 37 characters, so what is the probability of cyberbullying given that text length equal to 37 features? So that this is PC given Fi. And then we raise this to the weight, which I was just talking about, how confident we are in this particular feature. And this weight, mind you, was a combination of accuracy and fairness. Yeah. And how do we combine multiple such features coming together? So you kind of combine this feature I's contribution with whatever was available for all the features before I. So those are feature I minus 1. So until I minus 1, you've considered all the features. Until I minus 1, you've considered all the weights. You keep doing this progressively. You've covered the entire gamut of features. You have the P plus. Yeah, these are the confidence weights, as I was saying. You do exactly the same thing for the negative cues that you have. The probability of there not being cyberbullying, again, you raise it to all the weights available, and you will get this P minus. Now, once you have the P positive and P negative, you can combine them together to get this overall normalized version of probability of cyberbullying given the feature I or feature still I. And what you do is you take the P plus, you raise it to this agreement coefficient between features, and then which are being considered, and then in the numerator, denominator. Yep. On the bottom side, basically you normalize it by the p plus and p minus. Again, both of these have been raised or normalized based on the agreement coefficients. So together you'll get the overall probability of cyberbullying by combining all these features together while considering the confidence weights and the agreement coefficients. So what we did was we collected a data set, or rather we used a data set as collected by Hussein Mardi et al. In an earlier work. It had about 2,000 media sessions, as I was talking about. They were manually labeled by human beings with some instructions. 580 of them was labeled as non-bullying, 119 as bullying. But yeah, not all media sessions are still accessible. Some of the images have disappeared and things like that. So it's a smaller data set now. And further, we didn't want to focus on the aspects associated with imbalance. So we have created a subset, a balanced subset for our initial analysis. The number of features which I didn't get into, you are welcome to try out, read our paper and look at all the details. There were a number of textual and visual features created. Only a subset of them were considered based on this thresholding which we had for how much should be the feature score for each feature before it's considered part of the fusion framework. Our definition of sensitive attribute based, like the definition to create demographic groups, was we were considering media sessions where the image was only of a single male or a group of males, and everything else was considered not the privileged class. So we want the performance for these two groups to be similar. And the lambda, which kind of defines how much you weigh accuracy versus how much you weigh fairness, was basically computed empirically in terms of the maximum accuracy which was available on the training set. All right. Our results are as follows. Our results more or less say that, okay, when we compare three things, first one was naive Bayes, which I guess is the closest traditional approach. The second was our baseline being that it was this Bayesian fusion. It would use things like agreement coefficient and weights, but it would not consider fairness as part of computing those weights. So that's the second approach in orange. In effect, what it means is like lambda is 0 in our fairness versus accuracy, that combination. We give 0 weightage to fairness. The third one in yellow, that is our approach, where we found empirically the coefficient that lambda should be 3.89. What you will see in terms of accuracy, which we calculated using AUC, in terms of true positive rate as well as false positive rate. So AUC and TPR you want as high as possible, false positive rate you want as low as possible, that our approach at least didn't hurt the system. So compared to a naive Bayes or compared to fusion, but naive fusion where there's no role played by the notion of fairness, our approach, the one in yellow, kind of gave comparable or even slightly better results. Where our real contribution lies is on the other side, which is the bias levels were greatly reduced. They were significantly reduced in the sense they were statistically significantly reduced if you compare the privileged and the unprivileged. Visually speaking, you can see the delta between the privileged and unprivileged groups. For naive Bayes, it was close to 6.5%. For this fusion approach, but without caring for fairness, it went as high as 8.5%. But in the proposed approach, it was less than 0.5%. I mean, visually, you can already see the difference. The same trend was there for TPR, more or less the same thing for FPR. We compared, as I said, like to see a t-test to do the statistical significance analysis for the differences. And we found that in the naive Bayes as well as our baseline, more or less, we almost always found significant differences in the group, but the differences became not significant when we considered this combination, this combined approach, which valorizes both accuracy and fairness in making the decision. So to conclude, this, as far as we know, is the first attempt at a Bayesian fusion framework that not only optimizes for accuracy, but also considers fairness. So yeah, if there's only one thing which you take out of this talk, it is that it is important and it's possible to consider fairness when you are fusing multiple modalities together for a task. There's lots of need for future work. There could be more sophisticated methods used. Our Dataset was a single social media network, very small in size, homogeneous in size. So again, it could be done more robustly over different data sets. This could be applied to multiple applications. We thought cyberbullying, multimodal cyberbullying detection was a great first case for this. But frankly, this approach is generic. You could apply it to anywhere where you would apply a multimodal framework. We hope that the results pave way for a more accurate and a fair approach for cyberbullying detection. So as we are countering something as negative as cyberbullying, we also need to make sure that it's not just helping a particular section of the society and not the others. So that's the hope, and that's our contribution in this direction. Thank you.
Thanks, Vivek. It is indeed very, very nice work. So any questions from the audience? Okay, if not, then probably let me ask one question. So indeed, very nice work, and in fact, we are also, I would say, working toward the multimodal cyberbullying, trolling work, and so on. So one problem we face, the difference between cyberbullying, hate speech, and trolling. So would you like to comment on that?
So one, I would say that there are no well accepted definitions of each of these things. People kind of sometimes tend to be very inclusive and sometimes tend to be very specific in what they mean by each one of these things. One big difference between cyberbullying and the other terms which you said, including hate speech and trolling, is this notion of power or inequality. Another big definitional difference between cyberbullying and some of the other forms, and there are more, right? There's doxing and then, well, stalking. I mean, negative online content, there's a whole gamut out there. So power indifference is the biggest difference, which is typically adopted. And the second one is repetition. So power indifference means that the two people who are talking, often one person is a lot more central, is of importance to the network, has social power, some other notion of power compared to the other person. That's what is considered often like a major difference between cyberbullying and other forms of online abuse. The second one is repetition. And that kind of is very obvious when you look at like school bullying. That's where the term kind of comes from, that you were not just harming the person once, you were repeatedly harming that person again and again and again. In the online world, well, that becomes a little bit muddled, and people have argued you could like revisit the same post. It could show up, for instance, on your timeline again and again. Other people could forward, retweet, and so on. So the repetition does happen, but in different ways. So that's my understanding of where cyberbullying is a little bit different than some of these other negative online interactions. Any other questions or comments?
So I think Rajiv sir's laptop got shut down, so he might have left. So I guess if there are any other questions, can you please ask? Anyone from the attendees, you can put your questions in the Q&A section if you want. Okay, so I think there are no other questions. So can we move on to the next presenter? Thank you so much, sir. Piyush, can you please hand over the presentation rights to the next presenter?
Who is the next presenter?
Just a second, I'll check.
Hello.
Yes, sir. Yes, sir. We
Yeah.
are starting with the next presenter.
Yeah.
Could you please tell us who's the next presenter?
So the next presenter is Deep Dikshit is here. Is Dikshit, Ashwat, Devanik? Anyone from the?
Uh, I don't think they're
No,
in
no, sorry,
the
sorry.
No, sir, I
panel.
don't see them.
No, no, wait.
Okay, Piyush, I guess Akanksha is in the attendee list right now. So can you please move her to the panelist section?
Yeah, sure.
Just a second. Let's check which Akanksha is the presenter. Just a second.
Hello.
Yeah,
Hello.
so Akanksha Gautam is the next presenter.
Yeah.
Yes.
Akanksha Gautam. Yeah. So Akanksha, please try to wrap up your presentation in 15 to 17 minutes so that we can have questions for next 2-3 minutes.
Akanksha, are we audible?
Actually, the button which says
Ah,
my screen, it's not clickable to my end.
just a second. Just a second. Piyush, can you please try now, Akanksha?
Oh, yes, I've made her the presenter. I hope it's working now.
Yeah, it is.
Okay, thank you so much.
So, hello everyone. It's a long and interesting day. I would appreciate your patience and attention for a few minutes. I am Akansha Gautam, a final year undergrad student pursuing BTech in Computer Science and Applied Maths in computer in Indraprasth Institute of Information Technology, Delhi. I'm here to present our work titled SGG Spinbot Grammarly and Glove-Based Fake News Detection. So let's dive in. The first slide focuses about the statement of the problem. News consumption using online media has increased exponentially in modern society due to cheaper cost, easy accessibility, and rapid dissemination of information. However, it also encourages the spread of misinformation and hoaxes. If we will see the current situation, COVID-19 has affected our daily lives to much greater extent. Since the A recent research report of Science Daily blog showed that public engagement with false news is higher than the legitimate news from mainstream sources, which makes social media a powerful channel for propaganda. Therefore, fake news detection has become an important issue in this modern society. Now the next slide focuses about the challenges that we faced while working on a study. So to help mitigate the negative effects caused by fake news to benefit both the public and the news ecosystem, it was critical that we develop methods to automatically detect fake news. Detecting fake news on social media poses several new and challenging research problems. Though Fake news itself is not a new problem, but the rise of web generated news makes fake news a more powerful force that challenges traditional journalistic norms. Another challenge was to build a robust model that classify between fake and the verified content of online news from multiple domains and perform better than state of the art in experiments like cross domain and multi domain analysis. Many times, news is new, and such newness of news articles, be it legitimate or fake, call for robustness in the fake news detection problem. That is, fake news detection model should not be domain dependent. So this slide talks about the three intuitions that leads this study, which are Spinbot, Grammarly, and glove-based model. And now we'll try to understand each one of them in a bit of detail. So the first one is Spinbot. Spinbot is a free automatic article spinning tool. It rephrases the text by spinning textual data of length up to 10,000 characters in a single go. We use Spinbot to obtain paraphrased news articles. So let's say that there's a person with malicious intentions. Now that person will either use any paraphrasing tool or won't use such tool. So assuming that he is not scholarly, the article he will post would be very close to Spinbot based articles. If used article spinning tool, or it will be very distant from the Spinbot news articles in terms of the features. Whereas the person with no malicious intent, their legitimate article would lie somewhere in between. They would not be too close because such automated tools may not closely capture the writer's real intention. So this slide talks about the Grammarly, which was our second intuition. So what is Grammarly? So Grammarly is a proofreading application that uses artificial intelligence and natural language processing in providing real-time suggestions to mistakes in grammar, spelling, punctuation, word choice, and style. Grammarly provides numerous facilities like contextual spelling, grammar, sentence structure, punctuation, style, vocabulary enhancement, plagiarism, word count, readability, and vocabulary. And then the next question arrives, so why we use it? So we used it to extract mistakes-based features, assuming the English writing of the people who spreads fake news is not that really good. So the table that is present to you on the right hand side shows the extracted Grammarly features for both types of news, fake and legitimate. Now this table signifies how the Grammarly feature can help in distinguishing both kind of news. So the third intuition we had that is the glove-based model. So the glove-based model that we constructed is basically a combination of glove and K-means algorithm. Glove is a popular word embedding algorithm developed by Stanford NLP. It is based on linear substructures and nearest neighbor. The underlying principle of glove is the simple observation that ratios of word-word co-occurrence probabilities have the potential for encoding some form of meaning. So let's say you will give a word, so it can output a numeric feature vector of n dimensions. Now, since we need to classify articles, not words, we use a codebook approach to represent an article shown in the mentioned figure. So let's say there are m words in the corpus. So we use glove to convert this corpus into an embedding matrix. We then apply k-means on this embedding corpus to divide the matrix into k clusters of feature vectors. We then compute the means of feature vectors in different clusters and assign them as codes in our embedding code. The idea is to develop a frequency table depending upon how many times different words in an article fall close to different codes in our codebook. And this frequency table is what we later call as glove-based features. So in short, this picture says that so we basically started by constructing a embedding codebook using glove model for all textual data. Then for each article, we perform tokenization and use glove model to obtain word embedding. Later, we used these embeddings and the embedding corpus that was obtained in the previous step to build our frequency table using distance computation. We further name frequency table as glove-based features. So now I will talk about our proposed work. And how we utilize tools like Spinbot, Grammarly, and glove-based model to develop a robust fake news detection model. So this figure shows our proposed approach. So we started by paraphrasing the original articles and obtaining their corresponding paraphrased news articles using Spinbot. Then we extract Grammarly features for both the original and paraphrased news articles. Similarly, we obtain glove-based model features for both the original and paraphrased news article. In addition to these proposed features, we also extract some essential features like basic TF-IDF and emotion lexicon for both the original and paraphrased articles. So we basically extract a feature set consisting of 7 types of lexical features that include unique word count, stop word count, URL count, mean word length, and many more for each news article. Then we also extracted the unigrams and bigrams derived from the TF-IDF representation and also performed sentiment analysis on the corpus of the news articles using text blob. And then in the end, we concatenated all these features and then fed it to the random forest classifier to identify whether the news is fake or not. This slide shows about the classification results that we got from our study. To evaluate classification results, we use two publicly available benchmark datasets of fake news detection taken from the paper Fake Automatic Detection of Fake News. The first dataset is Fake News AMT, and it is collected by combining manual and crowdsourcing annotation efforts, including a corpus of 480 news articles, incorporating 6 news domains, which are technology, business, education, sports, politics, and entertainment. Whereas the celebrity dataset contains 500 news articles collected directly from the web. Now, below mentioned tables shows the five-fold cross-validation testing accuracy. So we basically achieve an accuracy of 78% and 95% on the celebrity and fake news AMT dataset when using all the proposed features. So it entails the fact that a proposed method predicts a high number of news articles correctly. So we further perform 3 experiments. So the first one is the learning curve experiment. So we perform this experiment to explore how the amount of data affects the classifier's accuracy in identifying fake news. What we did was we plot the learning curves for the proposed approach on both the data sets using incremental fractions of data and compare it to the state of the art. So these results suggest two things. So the first one is that our proposed method is outperforming the previous work, and the second one is that our learning curve signifies a steady improvement in both the cases. So it implies that a large number of training data has the potential to improve the model performance. Now the second experiment is cross-domain analysis. We perform cross-domain analysis to test how our proposed method helps distinguish fake news across different domains using all the features. What we did was we first trained our best performing classifier on the fake news AMT dataset and test on the celebrity dataset. Similarly, for the second case, we train our best performing classifier on the celebrity dataset and test on the fake news AMT dataset, and then record the results. So mentioned table captures the comparison of results obtained in cross-domain experiment and suggests that our method outperforms the previous work. The third experiment that we perform is multi-domain analysis. So fake news AMT dataset contains news articles of 6 domains, such as business, education, politics, technology, sports, and entertainment. So in this experiment, we train our classifier on the 5 available domains out of 6 and test on the remaining domain news articles. So, for example, to find out the accuracy of the entertainment news articles in this experiment, we train our model on the 5 domains like business, education, politics, technology, and sport, and test on the entertainment news articles. So, the table that is shown in the right side of the screen shows that our method outperforms the previous results. So, in this paper, we address the task of identification of fake news using online tools. So, we basically introduced 2 new sets of features, one obtained through Grammarly and another obtained through glove-based feature. Additionally, we introduced the paraphrase article in this problem. Our study shows that the usage of features extracted using Grammarly, Spinbot, and glove-based model with other essential features such as basic, ngram, and emotion lexicon improve the model performance significantly. The combination of these features achieved the best performance with random forest classifier. Our experiments show that our method outperforms the state of the art in all 3 experiments, such as learning curve, cross-domain, and multi-domain analysis. These results also suggest that our proposed method is more robust empirically than the previous works. So now in the end, I would like to thank my supervisor, Dr. Koteshwar Rao. Also, I would like to show my gratitude towards the organizing committee of the IEEE Big MM 2020 and the audience. So now we can start the Q&A session. So if anyone of you have any question, then let me know.
Thank you, Kancha. So we have room for 1 or 2 questions. Anyone?
Hello.
Yeah, we can hear you.
There
Please
is a
carry on.
question from Mr. Dinesh. He's asking, is this approach able to handle the cross-platform issue?
I'm sorry, I could not hear you.
The question is this approach able to handle the cross-platform issue?
Cross-platform issues. Yeah, so basically what we did was our method our proposed method shown that uh, for the dataset which contains a news of various domains, so for that thing our method can handle such kind of things.
Okay, thank you for telling.
Yeah, Sumit, you have one question, please. So Aryan, please make Sumit and in fact everyone as a panelist so that they can unmute themselves and ask questions.
Sure, sir, I'll do it.
Okay.
Yeah, Sumit.
Yes.
Thank you, Rajiv. Thank you, other members. Akansha, this was really a lovely presentation. I have a general question that you actually proposed this approach for fake news detection. So,
Yes.
yes. So, in broadly, in every news, there are basically 2 portions. One is the text, other one is the image. Let's suppose our image is basically contain these 2 portions. So, how you tackle the text portion as well as the image portion? Because the approach for both classifying.
Okay, so right now we have tested our model only on the textual data.
Okay, this is only for the textual data.
Yes.
So do you not think that almost all the news they are having some kind of image caption with that So it is not advisable. It is what's advisable to do or devise a model with containing both the things, text and the image.
Yes. Actually, we are working on that. So we will extend this project and will include the image part also in future.
Fine. Any directions, any suggestions for this combined approach at your end?
No, not yet. Sorry.
Not yet. Okay. Fine. No issue. No issue. Thank you. Thank you. Thank you.
Okay, so I believe there is no further question. So thanks Akanksha and Kuteshwar. So let's move to the final presentation for today. I believe Bhavya and Dinesh Vishwakarma will be presenting the paper. So Aryan, please make Bhavya as a presenter.
Done, sir.
Hi, good afternoon, everyone. This is Bhavya Malhotra from Delhi Technological University. First of all, thank you for having me on here. It's an honor to be presenting at this conference. Today, I'll be presenting my paper titled Classification of Propagation Path and Tweets for Rumor Detection using Graphical Convolutional Networks and Transformer-Based Encodings. So, for the outline of today's presentation, we'll be starting off with an introduction, followed by a proposed approach. Afterwards, we'll talk briefly about the theory of graphical convolutional networks. Afterwards, we'll follow with the data sets and experimental setups and the results of a paper along with all the comparable methods. And lastly, we'll conclude our paper. So I'll start with an introduction. So as all of you must be knowing that social media platforms have become an integral part of our lives, be it for sharing news or socially connecting, or for an entertainment purpose. So our lives have become more and more digital than ever. One such social media platform, Twitter, has extensively become popular for sharing news. As per the reports in 2020, there are around 330 million active users on Twitter. But as Twitter is rapidly being used to share news and information, it is also causing a problem which implicitly comes with the sharing of news, which is spreading of misinformation and rumors. So now, the question might come in someone's mind that whether fake news on such social media platform are pretty prevalent. So the answer is yes, of course. Such fake news on such social media platforms are speculated to have affected major events around the world, like presidential elections in the US or riots in India, etc. So that's why it's very important to discuss about this area of research. So since social media platforms have existed here for more than a decade now, and so has the problem of rumors and fake news, and many researchers have come forward to tackle this detection of fake news tasks. There are various mechanisms that have been suggested by many researchers in place. Some of the basic mechanism can be categorized into three types. The first one being a content-based mechanism. These are the features that leverage the content of the post. This could be either visual-based, like images, or text-based, etc. The other part of the other type of mechanisms are social context-based mechanisms. These are the mechanisms that focus on features extracted from users' social engagement. These mechanisms can leverage information about the network involved in spreading of a particular news. Another thing I'd like to add about social content-based mechanism is that unlike content-based mechanism, there's a lesser scope for tampering in propagation-based feature, so as to be able to deceive the detection algorithm. The other category, of course, is the newly built category, which is, you could name it as a hybrid mechanism or multimodal mechanism. These are the mechanism that leverages feature extraction from both of the above two mechanisms. I'd also like to take a moment to discuss about the deep learning methods that are in place. So as you know, with the deep learning era, these data hungry deep neural networks are performing groundbreakingly really well in these detection tasks because of the presence of data. So we have decided to go forward with the deep learning based approach. Now, another question that might pop in someone's mind is why, since this problem has existed since a decade and there are researchers in place that are working on it, then why does this area needs constant attention from the community? The answer is very simple. So, no, since with the advancement in fake news detection of technology, we need to understand that the creators of these fake news have also adapted to these advanced technologies to deceive current detection algorithms. So there's GPT-3 algorithm that's been talk of the art since past couple of months. So if we could understand that any text generated from a such a high data trained algorithm could easily deceive a normal content based mechanics. So that's why we need constant attention from our research community to tackle this task. So coming to our proposed approach, we in a paper we propose a novel method that for news that checks the trustworthiness of news tweets by extracting its structural properties of a tweet's propagation pattern through user involved in retweets and responding of a particular tweet, as well as the linguistic cue from the source tweet text. For the deep learning based methods, we have particularly used two neural networks in place. The first one being graphical neural networks, which is a part of geometric deep learning approach for supervised graphical classification, while the other one that we have used is recurrent neural networks along with word embeddings, transformer based word embeddings for tweets text classification. So an intuitive understanding of our algorithm would be that it tells that how a use of a specific class, and from class here I mean it could be of a particular class, means it could be it could be a fake news or it could be a true news. How these different news classes types of news of different classes spreads. What are the characteristics of types of user involved in spreading that news? And also we are also taking in consideration the linguistic view of the source news. So on the right hand side, you'd see a diagram here. That's a graphical structure. So for a social network, you could see that the first node here could be the user who has posted a source tweet, and all the other nodes are either the responder of the source tweet or they have retweeted the source tweet. We could model this as a graphical structure, and for each user node, that is each user who is involved in propagating this news source tweet news, we are extracting 11 profile features for them, and this is modeled into a graphical transformation for geometric deep learning. For the source tweet text that is present in our data sets, we are using Roberta-based transformer encoding to encode these into vector representation, which are further fed into recurrent neural network for text classification. But now we'll come to our architecture of our approach. So here you see there are two parts to the architecture. On left hand side, this is the text classification part, which has an input of source tweet text. On the right hand side, you see it starts with the input where where a user who has posted the source tweet has a propagation part built along with him. So along with him or her. So there are features associated with each user, which could be friends count, followers count, or either the person is verified or not. So these are the two modalities in this architecture. First, we'll look at the text classification part. So let's just say that there is a text tweet that has been posted. What our algorithm is trying to do is it uses transfer learning based approach from Roberta based training strategy to convert the tweets text into a vector representation. These are further fed into bi-LSTM layers. Uh, these are further fed into three bi-LSTM layers, which have TANH as nonlinear activation function and sigmoid as nonlinear activation function for bi-LSTM scale. We're also using, you can see we are using dropout here. So in our initial experiments, we had observed some of the overfitting. So that's why we have used dropout layers as well. We have also performed batch normalizations layers in our architecture so as to scale our vector representation. Now, once we have fed our vector representation into these layers, we get a output vector representation. And now, moving to the right hand side, what we do is we first convert the propagation part into a graphical matrix, which is of dimension n cross f, where n is the number of users involved in retweeting the particular tweet, and F are the number of features that I had just discussed about. We then feed this graphical matrix into graphical convolutional layers along with batch normalization. So for the purpose of supervised graphical classification task, we need to retrieve the vector representation for each propagation pattern. So what we are doing is we are using global mean pool layer and global max pool layer in our experiments to extract a vector representation of each graph, right? So another thing that we have observed is that as per our intuitive assumption, the source user who is posting a particular tweet would have higher weightage in deciding whether what class does a particular tweet belongs to. So an intuitive example would be that that the profile feature of a user posting a fake news. These profile features could be whether the person is verified or how many friends or followers does he have, would be very different from a profile features of user posting a true news. So that's why we have made this intuitive assumption and we have added the source user features here as well. So now that we have text feature representation, vector feature representation, graph feature representation, as well as source users feature representation, we are using a concatenation layer to concatenate all of these features together, and we're passing it to a fully connected layer along with a softmax non-nil activation function to get our outputs. So this was a proposed approach. Now, take some time to discuss a little about the graphical convolutional networks. So graphical convolutional networks are pretty amazing as per for the graph database. There have been different algorithms that have been suggested by the researchers for semi-supervised graphical convolution. The major contribution being from Thomas Encke and Maxwelling for fast approximate on convolutions on graph. The derivation is beyond the scope of this presentation, but we'll be discussing here about the intuitive example of how supervised graphical classification could be used here. So on the right hand side, you'd see that there's a graphical structure present. There are 6 nodes and there are edges that are connecting to them. So this graph could be depicted as G, and it's a representation that comes from its vector as well as edges. So we have a graph G, and for each graphical convolutional networks layers input, we have a given graph G, and we take in 3 inputs. The first one being an input feature matrix H naught, which is of dimension V into V cross F, where V is the number of nodes or number of vertices in a graph, and F are the features of each node. We have an adjacency matrix of dimension V cross V, and then we have a weight matrix of size F naught cross F1, where F naught could be understood as an input feature vectors, while F1 are the uh, output feature representation. So to get the feature representation of the first layer, we could model a graph as a function of as a nonlinear function of a h naught and w1. So generalizing this equation further, we could come across an ith layer for a graphical convolution layer, which could be a nonlinear activation function of a input header feature representation of I minus 1th layer and weight matrix of ith layer. So now that we have a graphical convolution layer in place, let's talk further about it. So there are 2 modifications into it. So the first thing that would be that needs to be understood is that for the adjacency matrix, what it does, it tells about the structure of the graph, that which node is connected to which other nodes. But we would realize that unless there is a self node in place, this adjacency matrix would fail to aggregate its own feature of its own input hidden feature from I minus 1th layer to compute hidden feature representation for ith layer. So what we have done is we have altered our adjacency matrix and have added a self identity to loop into it by adding an identity matrix in. Another thing that we have done here is that we have normalized our graphical convolutional layer using the spectral. This is mainly done as to understand that since there could be nodes with larger degrees, that means there could be nodes which are connecting to many other nodes, will end up having larger values in their feature representation. While nodes, vertices with smaller degrees or which connect to lesser nodes will have smaller values in their feature representation. So this thing needs to be normalized, and that's why we have used the spectral rule there. And that's how this is the final, the equation 5 tells us about the final equation that we are using for graphical convolutional networks. Right. Now, coming towards our data set, we are using two publicly available benchmark Twitter 15 and Twitter 16 data set. Both of these data sets are given by Jack Mao. We are constructing our data sets on top of these data sets. The original data set contains a file which has for each row which has tweet ID, timestamp, and source tweet text. Apart from this file, they also the original data set also contains a separate text file for each source tweet, which tells about the propagation pattern of each source tweet. This text file contains rows that correspond to two connected nodes. The connection between these nodes mean that the second node has responded to the tweet of the first node. And each node is represented as tweet ID, user ID, and timestamp. So now we'll look into the class-wise distribution of these data sets. As you could see that the classes are fairly distributed, and from the original data set, we are leveraging the source tweet text for the text classification purpose. Now, since the user-based profile feature were not available in these data set, we have constructed our own data set on top of it using the Twitter's API. We have extracted around 11 profile features of each user involved in spreading a particular tweet. The profile features are present in table 3. These could be favorites count, followers count, friends count, etc. We have also observed that there were around close to 5 lakh users present in Twitter 15, while there were 3 lakh users present in Twitter 16. So that's our construction of data set. Also in the original data set, we have observed that there were some anomalies, like some of the edges occurred twice, and there were some observed timestamps and negative values. So we tried treating them as well. For the train test split, we have divided our data set into 3 parts: train set, test set, and validation set. 10% of data set has been used for validation set, while there's a train test split of 3:1 for the remaining data. Now, coming at the experimental steps here, we have used PyTorch-based framework to design an experiment. The dropout is set in the range of 0.3 to 0.5, and batch normalization has also been applied. For the loss function, we have used cross entropy loss along with AtomW optimizer. The learning rate is set has started with 0.01 and is scheduled to decrease after specific step. The batch size has been in the range of 32 to 64, and early stopping has also been applied at the desired accuracy. Now, coming to our results, the table 4 shows the results for Twitter 15 data sets. The metrics used are accuracy, which is given by total number of correct predictions by total number of samples. We have also compared the class 5 F1 scores, which is trade-off for precision and recall. So as you could see that our algorithm is able to perform well in both accuracy as well as the class 5 F1 scores, and we are able to achieve state-of-the-art results here in Twitter 15 data set. For Twitter 16 data set, again, we are able to achieve state-of-the-art results. Our suggested algorithm is at par with the current state-of-the-art algorithm, which is the propagation path classification using RNN and CNN. So these are the result metrics table. Now we'll look at the accuracy versus epoch for both the data sets. So we'll see for the Twitter 15, we are able to achieve a stable accuracy at around 300 epoch, while for the Twitter 16, we are able to achieve a desired accuracy for at around 220 epochs. Here you could also see that there's substantial overfitting in both of these data sets. This could be attributed to the fact that the size of these data sets are pretty small. I mean, Twitter 15 is close to 1,500 tweets, while the Twitter 16 is even smaller. So perhaps a newer data set could help to validate our approach even better. So finally, I'd like to conclude my paper. So in this paper, we propose a novel method for the purpose of rumor detection and fake news detection that leverages textual features from source tweet. This helps to get the linguistic cue using the LSTM networks and Robert-based vector representation. The other important part is is extracting the user profile features and modeling the user propagation pattern into a graphical structure pattern to perform a supervised graphical classification task. The experiment shows that we are able to achieve the state-of-the-art results. We could conclude that the feature representation of propagation pattern can be modeled as a graph, and it's a way it's a way to go forward, since these couldn't be tampered as well, and they are very useful. So, yep. These are the references that I've used in the presentation. Again, thank you for listening. I'd like some time to thank my mentor, Dr. D.K. Vishkarma, for being the guiding force here. I'd also like some time to thank the conference host for giving me this opportunity.
Thank you so much. So any questions for Bhave?
Okay, so I think Rajiv sir had a power cut at his home. So are there any questions that anyone wants to ask? From the attendees, if you want to ask a question, can you please put it in the Q&A section? Okay, so I think we have no questions. So I think we can conclude the session. Thank you so much, everyone, for joining in. It was a great session. Thank you so much. We are ending the session now. Thank you so much.
Thank you. Thank you.
Hello.
Yes, sir. We concluded the session.
Okay, wonderful.
Yeah. Thank you so much.
Thank you so much. Thanks everyone, and thanks for staying so late. And many thanks to IEEE student chapter. Thank you so much.
Thank you. Goodbye.